Very good morning, participants. I welcome you all for the second day of ATAL FDP on quantum computing algorithms and machine learning. One second, sir. Just to give a quick recap of day one, what has happened previous day. Professor Apurva Patel has covered how quantum physics is influencing the new generation computation, discussed quantum mechanical properties and their relation with applications, which requires exponential speedup, quoted many research areas and highlighted the efforts in India towards quantum computing. Professor Tribikram Gupta has covered the essential quantum physics, which includes physics behind qubits, particle wave duality, photon polarizations, spin, theory behind quantum entanglement, and related physics experiments to show the working of quantum mechanics, and also highlighted few quantum control techniques. Mr. Abir Vaishnav covered the mathematical essentials, including vector representation of qubits, broad sphere, Dirac notations, qubit operations, single qubit gates, multi-qubit gates, Bell states. Given intro to IBM Qiskit, we are going to use it for today afternoon as well as for tomorrow afternoon for the practicals, covering quantum components. This is the brief coverage of yesterday's FTP sessions. Moving further, today we have with us from IBM Dr. Sheshashayee Raghunathan, giving a talk on quantum computing present and future. This is the topic I tentatively formulated. I gave complete freedom to Dr. Shesha to stretch according to the convenience. So industry and academic perspective, overall we expect how industry is working practically and what challenges they are facing and how academic can adopt this quantum computing, because we are all beginners. So kindly guide us in that. Following Dr. Shesha's session is a session from Dr. Archana Ravinder on the Doi-Josa and Bernstein-Vazirani algorithms today. And in the afternoon, we'll be having the quantum algorithms implementation of the IBM Qiskit. This is the overall coverage for today's FDP. So with this, I request Professor Minal to introduce Dr. Shesha to the audience.
Thank you, sir. Very good morning, everyone. I welcome all of you on the second day of FDP on quantum computing, algorithms, and machine learning. Today we have with us Dr. Sheshashayee Raghunathan from IBM. Dr. Shesha is working as a senior engineer at IBM India from last 11 years. He has completed his engineering degree from Bangalore University. Dr. Shesha has completed his master's from University of Southern California in computer engineering. He has PhD degree from Center for Quantum Information Science and Technology, CQIST, University of Southern California, Los Angeles. Dr. Shesha has been honored with Client Value Outstanding Technical Achievement Award by IBM in year 2019. He has published many research papers and patents in quantum computing field. Sir, we wholeheartedly welcome you here in RBC as a part of this FDP, and I request you to start today's session. Over to you, sir.
Thank you. Thank you for inviting me here, and I'm glad to participate in this platform. And I wish all the participants had a good sessions yesterday, and hope that you will have a good session today and the forthcoming day tomorrow. So I hope to give you a perspective, mostly an industry perspective on quantum computing. And my hope is that I will have time to discuss. I would like it to be as interactive as possible. I have quite a few charts, but I don't intend to cover them in detail, but I'll try to cover as much as possibly can. But before I get started, maybe the host can tell me the time I have. I can go till 11:15. What is the plan here?
Till 11, you can have the session. So afterwards, also we keep taking the questions in between. Also, we requested the participants to keep pasting questions in the chat, and one of us will moderate, sir.
I think that will be great. So what I'm going to do is from time to time, I'll try to pause. If I don't pause, but if there are a bunch of questions that get accumulated, please do stop me and I will take those questions. I'll try to keep it very high level and try to, hopefully I'll finish it by 10:30, 10:40, so that we have another 15 minutes at the end to take as many questions as possible, unless we have more questions along the way. All right, let's get started. So hopefully you can see my screen. So as was introduced, my name is Sheshashayee Raghunathan. I'm going to give you a perspective on quantum computing, a brief overview, and also try to answer some high-level questions. What is it? Why it is important? Where we are? Where are we going? What does the roadmap look like? And things along those lines. So there are many challenging problems that are out there, computationally challenging problems. Be it in agricultural space, be it in manufacturing, logistics, or in deep science. All these areas have problems that requires pretty much a significant amount of compute resource to do it. And some of the problems, or many of those problems, are either NP complete or NP hard, which means that you can't solve them practically. You need to have some heuristic solutions. And thus far, in the last 50, 60 years, we've had significant development in the classical hardware. The speeds have increased, the performance, the efficiencies have increased, and it's become ubiquitous. But the fundamental model of compute is the same. So there is no new major compute model in the horizon that is fundamentally different from what we have in classical hardware. Even the GPUs and all the other things that we have is fundamentally classical, and it works out of the basic principles of classical hardware. So it provides a boost, and it has generated significant amount of industry around those computes. However, the model is still remain the same. Quantum compute offers a potential to address some of these hard problems. It is a fundamentally different model of compute. We will see some of that shortly. And it is very different from, at a basic level, very different from what classical is. So we're going to see some of what are those differences at a broad level, and then what it means and how we are developing along the lines. So this interesting new model then offers certain specific set of capabilities. There are some set of problems that it can solve efficiently that classical cannot do. And those problems include things like improved nitrogen fixation. So for example, this particular problem, this is creation of fertilizers. It is estimated that anywhere between 1 to 2% of all energy resources that is generated, particularly petrochemical, is used in creating fertilizers for the world. And that's a significant cost overhead. Imagine the kind of impact it can have on the environment, just this manufacturing of this fertilizer. What is the challenge there? So the idea of fertilizer is obviously to have a better nitrogen fixation so that your yield improves. And so the problem there is to understand how the nitrogen fixation process works. We know that many things in the real world, be it earthworm or any of those microorganisms, can do this more energy efficient and more better way. We don't know how they do it, but they seem to do it more efficiently. So the question then is, how do we understand? Can we borrow what nature is doing and maybe do it better? The challenge, of course, is that in order for us to understand that process, it takes significant amount of compute. In many cases, we cannot practically compute them at all. And so you are stuck at the point where you cannot understand the process, and therefore you cannot emulate what nature is in some cases doing more efficiently. The other is, say, for example, in the manufacturing, there is a lot of challenges in making CO2 conversion to hydrocarbons more efficient. So this is important because manufacturing can lead to a lot of pollution. If you can have a catalyst or design a catalyst that can capture CO2 and convert them and make it more efficient, therefore the emission is reduced. Carbon dioxide or carbon monoxide be the case, as the case may be. If you can trap them and hold it, we are probably going to be more energy efficient and therefore reduce the pollution in the atmosphere. In the financial sector, the challenges that there are challenges on understanding, coming up with better financial models to understand, to improve the stability and predictability. So this is a very important thing. As we saw in 2008 financial crisis, we didn't have sufficient models to keep track of what was happening in the financial sector. In any case, we need better financial models to be more stable in the economic sense. So these are challenging problems. This again is a problem that is not easy to solve classically. In many cases, the problem you cannot solve them efficiently if you want an exact answer. So you pretty much are limited by the compute capabilities of the hardware at hand. Now, when I say compute capabilities, I mean the best supercomputer that you can throw at it. The problem is the question of complexity. It grows exponentially fast that even if you throw a supercomputer at it, it's not able to handle that. Or come to the micro case. So we are in pandemic times. As we learned in the last year, finding a new drug is a challenging exercise. Apart from the process of taking the drug through the system validation, verification, identifying the drug, designing a drug, designing an antibiotics. All these are hard problem to do to a large extent because these are complex molecules, and complex molecules are hard to simulate exactly in classical hardware, which means that there is no way but to beyond a point do trial and error, actually build those molecules in the laboratory, try it, and if it fails, then go build something else. You do use supercomputers to get some initial states, narrow down the domain to search, but after some point, you will have to go build these things in laboratory and try it. Quantum computing can potentially do some of these simulations and if not solve it, but at least move the ball quite a bit so that you can do a lot more simulations more efficiently so that the time taken to figure these things out is much, much reduced. So why quantum? So this is a cartoon indicating, just giving a picture of what this game is all about. The section in white, you can think of those problems that we can do efficiently today. Section in light blue, think of those problems that are very hard to do. And dark blue is the domain that quantum is opening up. These are problems that are not easy to solve classically. And these problems, this is an active area. The frontier is ever expanding. New things are being discovered. And so this area is what is the space of quantum. What you can see is that it cannot solve all the problems, all the hard problems, but it can solve some amount of problems. But some of these hard problems typically has a large blast zone, which means that you solve one problem, you will solve a class of problems together, and its impact in real sense is quite dramatic. The area is, as I mentioned, is ever expanding. We are looking into more and more harder problems, more interesting applications of these hard problems are along the way, and more interesting research is coming and more sophistication is coming into this field. So what are the quantum applications? Three broad areas is where the application we are seeing. This is general categorization. So one is in the simulation, and this is probably the nearest in terms of a potential breakthrough application where we can hopefully see a quantum advantage. What this means is that simulating quantum systems in many areas of natural science, quantum chemistry, material science, healthcare sector, I'm putting that in natural science, though it's not exactly natural science, high energy physics, life sciences. The problems there involve simulation of molecules. So take, for example, a drug discovery example that I was telling you about a little before. The drug discovery, let's say in the we have certain virus and we want to be able to handle that efficiently. And what is needed is you need to identify a molecule that can go grab onto the virus perhaps and do certain things based on certain markers that they look for. In order for to design that particular molecule, it's complex molecules. And if you want to go figure out what is the right structure of it, we cannot exactly simulate those systems. And for us to be able to understand that process of the molecule, what it behaves, what are its properties, etc., we ultimately have to go build it. If we had a quantum system and the molecules, as you know, are described by quantum physics, if we have a good enough mapping, then we can potentially simulate that using our quantum hardware and it's more likely to do a reasonable job compared to certainly the classical hardware, and hopefully simulate those kind of molecules, therefore giving us better insight into this. So there is a class of problems. So this is in the space of drug. You can think of the same things in the case of materials. We are trying to discover new materials perhaps to do certain things, or maybe even look at certain materials to do specific operations for us, like say better batteries, etc. So those are the kind of research where simulation is the primary motive. You are trying to use quantum computing to simulate something else, particularly in nature, some certain molecules or collection of molecules. The second category here is artificial intelligence, but this is generally a broad stroke. It could involve optimization problems also. We put optimization Monte Carlo as a third category, but artificial intelligence and optimization have similar or overlapping properties in terms of what it does. You have linear systems, many times modeling and training. You would want to be able to do a better modeling and training. Quantum systems can potentially do certain things better. You have exponential state space available, and therefore perhaps you can do a better classification or more efficient with less positives, perhaps false positives. You can do a better, potentially a better pattern recognition or a fraud detection. Again, it's about classification problem. So you have a class of problems in the artificial intelligence spaces, and you can sort of map it to different use contexts. These are general models, and based on the particular application at hand, you can have various applications derived out of these approaches. The third category is the optimization or Monte Carlo approaches. So Monte Carlo, there are two different things here. They are not one and the same. Optimization, you would want to be able to, the world is full of optimization problems. Everything is a hard optimization problem that we have. In this example, we are citing portfolio optimization perhaps. And you can find a number of these optimization problems, network flow problems. You will have a whole lot of optimization problems everywhere. Those are the kind of problems where it is hard to do classically and it scales quite rapidly. There is possibility that quantum can provide some benefit there. And broad optimization, once you have constrained optimization problems to be addressed as well, when we have algorithms on that space, unconstrained and constrained binary optimization problems, you can then have a wide blast zone. Optimization has significant impact across the industries. The other category of Monte Carlo is the space where typically things that are unknown into the future, things that involve, say, risk analysis, for example, you would want to be able to predict what the future looks like. The way we generally do it is through simulation using Monte Carlo technique. And what quantum provides is potentially a polynomial benefit. In other cases, you potentially are looking at exponential benefit. In this case, we are potentially looking at a polynomial benefit. We know from Monte Carlo techniques that the convergence of Monte Carlo goes like 1 over square root of n. And in quantum, it was demonstrated that the convergence goes like more like 1 over n, and therefore you get a polynomial benefit. So what that means in real sense is that given a threshold, you probably need a lot less sampling to get to the answer as compared to a classical approach that we take. It may take a lot more sampling. Though polynomial in practical, in real sense, it may make a big difference. In financial industry, for example, they may run some of these Monte Carlo based risk analysis for days on end. That may, if it reduces to say a few hours, that's a big game changer in that industry. Some specific examples. So this is a joint work with Daimler. A lot of auto industry is interested in working with quantum or exploring quantum, primarily from battery research standpoint. So this is a joint work with IBM and Daimler, where lithium sulfur molecule was explored. As you know, lithium-ion batteries are the current default standards. Now there is a lot of movement in exploring other molecules. What they are looking for essentially is what are the properties of those molecules. So ideally, we would want to be able to store more energy in a compact volume. That's the idea of a battery thing. So which molecule affords us to do that? So they are now exploring different molecules and their properties that will lead them to understand which works better. And this particular work was on lithium sulfur. The other work in the finance sector is another application area I touched on a little before. This was a joint work with JP Morgan Chase and IBM to do it's a quantum amplitude estimation based technique where they did option pricing, which is a kind of a call option pricing is a way of it's a financial instrument in the stock market, which is used to do certain trading. So there they showed that you get a quadratic speed up using quantum over the classical approach. The other one with ExxonMobil. So this was advancement in using quantum computers to do some calculate some thermodynamic observables, and they showed that the quantum can help the next generation tool of chemists and chemical engineers. Their focus is to understand there are many problems in the petrochemical industry, including making it greener or identifying where the available energy source is. How do we transport them? There are many such problems. In this specific problem was to look at the thermodynamic observables that was needed by their chemists and chemical engineers in their area. Okay, before I go further, let me pause for any questions.
Audience, any questions? You can put it in chat box.
If there aren't, I'll keep going. We'll stop at appropriate time. I'll take another pause in a few minutes. Okay. So those were some of the applications, some recent developments that we are seeing, three broad areas that we saw. But if you take a step back and look at the quantum computing as a compute model, it's the building of it is still at its initial stages. The hardware that we are trying to build. If you see this picture, this is very illustrative picture. The picture on the left was from 1944. I think that could be an ENIAC machine. On the right is the quantum hardware. This was circa 2019. So we have moved much further along since then. But you can sort of see that it is still at its infancy. It's not so advanced as the classical counterpart, but it's developing quite rapidly. So then the question is, how rapidly? So on the left is the Moore's law. This is from Gordon Moore's original paper from 1965. On the right is the quantum volume metric that track. Quantum volume, think of a quantum volume as a metric that sort of tells us what is the capacity of a particular hardware. What we want is higher the quantum volume, more the volume, more the capacity of the hardware. So on the left, the prediction was that it's going to scale exponentially. Look at the metric was in the log scale, so the scaling was exponential. On the right is the same thing. We have the log scale on the y-axis. So a linear thing on the plot means it's growing exponentially. So what you're seeing is every year we are doubling, and in the recent year, we are growing at much rapid pace. We have 128 on the cloud, working towards 256. So you are seeing that the quantum volume is essentially doubling. It's growing exponentially. One of the reasons why there is a lot of interest in this area is this trajectory that we are seeing. We were growing fast, but now we are going in a much faster rate, even in the exponential. It's hard to say whether it's going to be in this line or somewhere here, but it's certainly above the x equal to y line. So we are doing much well in terms of the exponential growth, and it's likely to continue. We don't see a major technical roadmap in stopping us from this growth. So we are likely to see this growth for some foreseeable future. And inside the chip, so this is the actual hardware. The picture that you see is of what we call as a QPU, quantum processing units. These boxes that you see, these are the actual qubits. And this qubit, if you see the representation, the slice of it, you will see these things. This is the Josephson junction here and the two capacitive plates that provides the anonymity. And the Josephson junction is shown by this particular picture. These are the resonators to talk to this qubit from the external world. This is the microwave bus resonator. This is the quantum bus resonator talking from the external thing. And then you have the bus resonator that talks between the two qubits. The connection that you see between this means that there could be a 2-qubit operation between these two. You can see similarly a bus resonator connecting this qubit and this qubit, this qubit and this qubit. But then you don't have a direct connection, for example, between this qubit and this qubit. So those are some of the limitations of this particular technique. This is superconducting qubit-based quantum bit. So superconducting qubit is an artificial atom. Think of it as an unharmonic NC oscillator. And the lowest two energy levels are seen as the qubits values 0 and 1. So what is the scaling? This is the roadmap. We have been, as we mentioned, the quantum volume is increasing quite a bit. And you can see that trajectories along the way. So this one is just showing the number of qubits as an indicator, but not necessarily the quantum volume. We are going to see quantum volume as this number of qubits increase, quantum volume also increasing. Quantum volume is more an abstract metric, which has a dependency on many things, including number of qubits, the connectivity, the fidelity of the particular qubit, and the gate operations that it performs, the errors, etc. All is factored into that quantum volume metric. Here it shows the actual qubits. Ultimately, we need the number of qubits to increase. It's an important metric to track. And what you're seeing is different names that you see: Falcon, Hummingbird, Eagle, Osprey, Candor. These are all different generations of the hardware being released. And there are certain key advancement that happens in each generation. Currently, if you go to IBM quantum computing platform, you're more likely to see Falcon and Hummingbird. You're likely to see Eagle processors coming through this year. And then we'll be working on the next generation Osprey and certainly Candor. That's likely to come in another couple of years. At each point, key development or progress is happening. That's why we distinguish between different generations. All these are needed for us to scale up the processors. So we want to be at millions of qubits by the end of the decade, or around the end of the decade-ish. Then we need to scale it and solve some key technological problems along the way. And those are the problems that are being done as key advancement in need of each of these technology generation. So what we are expected to see is that in another couple of years, you're going to have processors which have 1,000 plus qubits. Quantum volume, given the quantum volume trajectory we saw, is also likely to be 1,000 plus. And that is a regime where some non-trivial problem can potentially be solved. Once we have these many qubits plus the quantum volume indicating the quality of those qubits, amongst others, will give us sufficient horsepower for us to be able to address some real problems of interest at scale, and therefore thus hopefully showing quantum advantage. Okay, so let me go to the next. So here, so in order for us to proceed along the way, so this is what is called as a super fridge. In order for us to get to 1,000 qubit processors, we need to be able to stack them. And what you're seeing, this is a 10 feet fridge. If you go inside, you'll have a good 10 feet between them. You need that in order for us to go stack some of this hardware to build those 1,000 qubit machines. It has to have 10x the cooling power. And you can sort of see that the cabling can be done from both sides. In the original picture that we saw from before, all the cables were running from top to the bottom. Now you can do from both sides. And that's how you could start stacking things up. Then you will have much more efficient cooling, and you need this kind of volume for us to be able to fit in and start the integration of more and more qubits into the system. So this is very well underway, and this is very active area of development at this point in time. All right, before we get into what qubits and quantum circuits are, let me pause and check if there are any questions.
Hello, sir.
Okay.
Here we have a couple of questions.
Uh-huh.
Yeah, so the first question is from Dr. Hitesh Shah. How AI related to quantum computing?
So I will explain that with an analogy. I can ask the same question. How is GPU related to AI? So what does, for example, GPU do? It does certain metrics processing, right? It does some of those vector and matrix processing efficiently. So a typical problem, for example, that you get in matrix transformation is a diagonalization of a matrix, which is in general hard to do as the number of n increases. And that problem gets, and more than diagonalizing, substance or aspect of interest, for example, is finding the minimum eigenvalue. It's one of those important problems that is typically used in optimization, or also you can think of if based on the problem, I think some aspects of AI could map into it. Now, what does GPU do? It does certain some of these matrix transformations, vector processing more efficiently than your CPUs can. Because the hardware is specialized hardware, it does certain set of computations to give you benefit. QPUs, quantum processing units, much like its classical counterpart, is doing something similar. So finding a minimum eigenvalue, for example, could be done more efficiently in quantum because the quantum is a linear system. And if you map your problems into a quantum system and have it evolve in a certain way, then you can sort of read out the minimum eigenvalue of that particular matrix. So if you have a more efficient way of doing it, a more precise way of doing it compared to your classical, that's the value proposition. So the physics of it, the actual implementation of it, we shouldn't mix up for what exactly it's doing. It's solving a matrix problem for us. And that problem you can always map onto it once we have a pipeline of transformations to take it from your classical representation of your matrix to the mapping in the physics that understands, that is Hamiltonian. That transformation, once that is done, you solve the problem in another domain, get the result, and translate back. You're solving the problem of interest.
Okay, thank you, sir. Sir, one more question here. Would you rely on cryogenic cooling to control decoherence, or is there any other method of cooling being considered?
So it depends on the technology. For superconducting qubit, we need to be at quite a low temperature. There are other technologies being explored that may have different requirements in terms of cryogenic profile. In our case, we have to, for superconducting qubit, requires us to be in the regime of 10 to 15 millikelvins. As time progresses, as we have better understanding, maybe new transmon qubits perhaps, that may move up. We do want to move up in the temperature scale, but there are fundamental limitations in the current technology that we have to be in that temperature regime. So in superconducting qubit, yes, we have to be in that regime, so cryogenic becomes necessary.
Okay. One more question. Is there any open source project supported by IBM for us to contribute?
Okay, I'll touch on that at the end. The whole SDK or software stack is all open source. I'll talk about that at the end.
Okay, sir, we can continue the discussion.
All right. Okay. So now, so we sort of motivated why quantum, and we then saw what are the problems that the industry and others are exploring at this point in time. What is the value proposition? Now let's have a brief overview of what it is about. So the technology is fundamentally different from classical because it is different at the very fundamental level. As you know, any compute that we do ultimately has to be translated into bits because your hardware understands only bits. If you look at that basic element of your classical compute, which is a bit, has two states, 0 or a 1. Quantum also has two states, but the model is fundamentally different in that you could be in any combination of 0 and 1 in a probabilistic sense. It is a fundamentally probabilistic model of compute. And nature is such. If you look at quantum physics, it's coming out of quantum physics. We know that nature at that level, at the fundamental level, is probabilistic. it is not exactly 0 or 1. It can be in some combination of 0 and 1 in a probabilistic sense. But when you do measure it, you will get either 0 or 1, and therefore you have to do sampling, and then you get the probability distribution of being in 0 or in 1. On quantum side, if you see, you will get something like this. This is a quantum circuit, which is built on those qubits. Each row here stands for a particular qubit, and time flows from left to right. And this is a particular qubit. We have 4-qubit circuit. These are the red ones are 1-qubit gates, and the blue ones are 2-qubit gates or entangling gates. You need these 2-qubit gates to do entanglement, and that is necessary the necessary things, because entanglement is a key quantum property, which is fundamentally coming out of quantum physics, that is unique to quantum and is not, you cannot produce that in a classical environment or a classical system. And that is the key differentiator between quantum computing and a classical computing. There are exponential number of these entangled states. So exploring that state space is the key element, key differentiator in terms of the properties. The superpositions, the interference are doable in classical mechanics, but entanglement is not there, or you cannot get that in a classical system. So these entangling gates becomes fundamentally important. These gates are unitary gates. They sort of rotate. All they do is rotate in particular dimensional spheres, if you want to imagine it that. And finally, on the last is this odometer type thing. That's what is called as a measurement, or you need to read out the system. We cannot read the quantum state at a particular point in time. We don't have access to it. Only thing that we have access to is when you do a measurement, you get the probability value. And that probability is what is accessible to us. This quantum state is not directly accessible. When you measure, everything becomes a classical string. So for example, if I was in some quantum state, imagine this to be a quantum state just for illustrative purpose, I could be in any points in this sphere. Think of this as a sphere. When you do measurement, either falls to 0 or drops to 1, and I do n number of times, I get a probability distribution for that. So it tells us that, okay, so I was in the state where probability of 0 was say 0.5 and probability of 1 was 0.5. So I was in the equator state. So then I understand something about that. But a given particular measurement will give you a particular bit string. If I have 4 of them after measurement, I could get 0, 0, 0, 0 or 0, 1, 0, 0. I could get any of those. Then you do n number of this, and then you get a sampling of it. Then you get a distribution amongst the state. A quantum algorithm takes the input, performs the transformation in the quantum space, and then finally uses these interference effects in a way to converge on the right answer, so that the probability of the right answer becomes significantly different from the other probability values, and therefore we will be able to identify the right answer. The quantum volume in a way also is a way to say, as long as the right answer is beyond certain good amount of threshold, then I know that the efficacy of the circuit is good. So the idea is always how to use these transformations effectively so that the right answer is increasing. The other thing that is of current interest is we can't go too deep into this circuit because of limitations of the lifetime. I've not shown that. The quantum qubit retains the quantum properties for a certain amount of time. After that, it starts dropping and noise becomes prominent. So you would want to keep them as shallow as possible. So some of these are current limitations. As you very well can imagine, as we improve the quality of the hardware, the lifetime increases, we can retain the quantum properties for longer and longer and longer. And therefore, we can potentially do more deeper and deeper circuit in time. But at this point in time, we want to limit the depth of the circuit. So bit versus qubit. On the left column, the first column is the number of qubits. On the right is if I want to do the same simulation in classical, how many bits are needed for me to track all the states. Note that the states represented by qubit grows like 2 power n, where n is the number of qubit. So if and the physical representation, remember each of those alpha 0 plus beta 1, if you had written it out, you would have learned that yesterday. Alpha and beta are complex numbers. And if you take complex numbers and their representation in classical, you would need something like 256 bits for each complex, because you have a real and an imaginary part. So you will have 4 numbers. you can sort of calculate this out to give us 512 bits that is needed to represent 2 qubits. And if you start increasing them, you will see that the number of bits needed to represent all the state space grows quite a bit, while quantum bit grows linearly, the classical bits is growing exponentially. And that's the key differentiator. The state space that qubits represent is exponential, and you cannot pretty much, beyond a point, not track it exactly. For example, if it is 160 qubits, you require all the atoms on planet Earth to be able to represent that. So which basically means it's impossible to do. All right, so let me pause there for any other questions before we go on how to do a computation on the current hardware. Any questions?
Okay, here actually the question was how qubit is different from binary, fuzzy, and rough set, but it is already, I think, covered in the last slide. Yeah, and one more question is Monte Carlo is a simulator?
Monte Carlo is a technique used to do simulation, and generally Monte Carlo simulations is generally used as one phrase, but it's a technique to do different simulations typically used in the scenarios where you have to predict something in the future. So it sort of traces different trajectories along the way, and then it averages over all the different possible evolutions to get a distribution on what is the likely model to see in the future. And this is, you can sort of immediately think of finance sector, where risk analysis is one classical example of it, where you have certain portfolio, what is the risk of your portfolio? You can ask risk on many aspects of the life. Anything related to risk, for example, involves us to peep into the future and predict the future. And typically, beyond the simplistic distributions, you will have to do Monte Carlo to do those simulations and then get a distribution from it. And then that is what is used to do certain prediction.
Yes, sir, that's it for right now, I think.
Okay, so now we saw the basic difference, the qubit. How do we program it? What is the workflow? So here is a short video. So on the left is a developer, us, sitting on our laptops perhaps. Then you have a cloud, and then you have the quantum hardware in the cloud. So you're going to see how things flow. So you have your program. You end up programming, say, think of it as a Jupyter notebook. Once you're done, you compile and send it across. That thing goes into IBM Cloud, gets processed. There is transpilation happens. Quantum circuit is generated. That then goes to a particular hardware in the cloud. It executes. Then once measurement is done, you get a classical string, and then it comes back. And then you get the result. Here it is shown a little simplistically, but basically we'll have to run it a number of times to get the right sampling, to get the distribution. So that is the current workflow. This is slightly changing. We'll touch on it shortly, but that's how you currently go program the quantum hardware. I'm going to skip this because I talked about this in the initial part. So what is the programming model coming through? So we are working towards what is known as a frictionless developer model. Basically, in the next couple of years' time, programming a quantum computer should be as simple as load the data, get the right permission. Once you have that, load your program and run it. It should be as simple as programming it. This is what we envisage in a couple of years. Once we have sufficient hardware, and also we need to develop those platforms to get us there. So what this is a frictionless model. So currently we are used to developing in certain things, certain tools, and we want to use the same tools in quantum so that there is no difference. The same languages used is what we also want to use. In our case, the platform, the software development kit built on top of the hardware is Python based, and all the tools that we use there is very much the same tools that are used in the Python framework and the libraries therein. And then the same code. The coding also shouldn't look very different from what we currently see in our classical programming. So that is the frictionless model, and that's what we are working towards. It's already quite a bit thereabouts. More needs to be done, but we are, as I mentioned, Python based, and we are using the same set of tools and languages, and the code looks very similar. And I'll give you pointers to go have a peek at it. Okay, so the ecosystem. Now, what kind of developers are needed along the way to take this platform? Now, in the last decade, the quantum computing, particularly on the software stack side, the SDK side, um, it was pretty much the same folks who are building the system or the ones who are developing that as well. That is changing now in the sense that it's gotten certain maturity, and now you need specialized skills along the way. Imagine the classical workflow in the classical developers. You don't program at binary level anymore, right? You program at your high level. You trust the appropriate compiler to take to the appropriate platform, map it to the problem, do it efficiently, run it, and get your results back. But then there are different skills at different levels. So you could be an application developer doing, say, C++, Java programming at a high level. But then once you translate it, there is a compiler. There is folks who specialize in compilers, who know optimization in the compilers. Even within the compiler, there are different layers. You have a technology independent layer where you do optimization at a pretty much at a graph level, independent of the particular instruction set architecture you are targeting. Then you may have a technology dependent optimization, which instruction set architecture using, which version of it, what are the instructions available, and you do optimizations around it, registers, or what is the cache size, etc. You can do optimization at that level. Then you go to the machine level and then you actually run it. Along the way, there is OS layer also available. So you have different skill sets coming into play for all these things to come together based on the role at hand. Much like that, kernel developers are the ones that are closest to hardware. So you have the hardware, you have certain properties of the hardware. Kernel developers need to understand that property. And their goal is to create a high efficient, high performance circuits using the knowledge that they have. They will be at the pulse level. They would want to maximize the performance of the particular hardware at hand. And so they need to understand how things work, what are the key features in the particular generation of the processor, and how to then abstract that out into circuits that then can go feed into the next layer, which is an algorithmic layer. So algorithm developers take certain circuits, the high performance circuits that are given by the kernel developers as a given, and then they build on top of those models. They then build algorithms on top of it. So here you get a circuit template from the kernel developers. Those needs to be stitched together into a higher level algorithm. And those is the work that algorithm developers. They need to have some understanding of the hardware, but not a lot. And they need to have certainly good understanding of circuit and that behavior. So we have sort of abstracted out the details of the particular qubit into a quantum circuit. They need to understand quantum circuit. They need to understand algorithms better. And they would want to, they need to be able to map the circuit to a more high efficient algorithm that can come out of those given circuit. Then comes the model developers, which is the highest layer. And these are the layers where you are no longer dealing at the circuit level, but you're dealing at the algorithm level or at the library level. You want to use different types of algorithms on different use cases. You're looking at different applications. In that domain, you're more outward looking, trying to say this algorithm will solve this kind of problems better. So then you start off looking at it there. Here, you will, the kind of skills needed is to be able to program these things, understand the algorithm at a high level. You don't need to understand certainly at the quantum circuit level. That gets abstracted out. You get the algorithmic level, and then you should be able to understand the domain at hand. So you could be a subject matter expert in a particular area. You should be able to understand what this algorithm means and what kind of problems in the application domain is likely to benefit from it. That mapping is what the model developers are likely to do. So we expect that there will be separations, there will be specialized skills coming in these areas, and there will be stacking of these different skill sets. So what will it make practical? So from the quality, the capacity, and variety. So all these three are important for us to be able to have industry relevant workflow. So quality is how well are the circuits implemented in quantum system. This is the low operations errors, the fidelity of the particular gates, what is the quality of the quantum qubits that we have, etc. How many of them are run? Because this is the question of scalability. So we need to have seamless synchronization between quantum and classical. That is the current working model that we are looking at. It is a hybrid algorithm. That's the model that is likely to come through, that is likely to have a solution embedded in it. various different kinds of dynamical integration of this quantum and classical operation, so that you can reduce the overall overhead. So if you put this back together, I'll come back to this, some of the recent capabilities that are coming through. So dynamic circuit, for example. So in order for us to be able to achieve what was described previous page, is the workflow that I showed in that movie was where you have a laptop, you program it, send the circuit across to the cloud compiles it, makes it efficient, and send that as a job to the quantum hardware. It executes it, it gets the results in zeros and one. That is the current workflow. What we are working towards is a more iterative workflow locally. Many a times you would want to be able to measure certain things based on which you can do certain operation back and forth. There are new latest algorithms involve quantum classical hybrid algorithms. So what you have is quantum running, and there is a classical hardware close to the quantum. It's going to do back and forth iteratively and solve the problem of interest, and then give you the result back afterwards. This portion, the dynamic portion of going from quantum, you measure, so you're in classical space, and then you're going back. Think of it this way. The models that are emerging, the more modern algorithms in the quantum space, is hybrid algorithm. You have a quantum circuit that's going to do certain job. You have a classical, and this is a parameterized circuit. And the classical computer uses classical optimizer and solves for this parameter. And it tries to find the optimal parameter that does the job. And the cost function defined in this optimizer embeds the particular problem at hand. It solves for that problem. Think of it as, for example, finding the minimum eigenvalue of a particular matrix, for example, that gets mapped into this cost function. We don't know what that value is, so we have initial trial state, then you, which is parameterized. Then you tune the theta of the parameters, and that is using the classical hardware. The actual run is done by quantum. And this is the working model that is coming, and a lot of algorithms have come using this basic principle. What that means is that you need to have back and forth between quantum and classical, and that's what is happening in this particular loop. You're measuring and doing course correction and doing some change, and then you're putting it back. That's in the parameter tuning model. And there could be some error correction and mitigation techniques also coming in. There could be many uses of this particular technique. So we are moving from this current bulk model where you create the circuit, run it, get the result, create the circuit, run it, to a more dynamic workflow. And this is what will be needed for running some of the more modern algorithms. So this dynamic circuit is demonstrated already. It's not in production yet. We probably will have this in production latter part of the year or probably in next year. So for example, the mid-circuit measurement is another capability, which is an important capability in order for us to be able to do it. So one of the limitations right now is for sampling. Remember, the quantum circuit is a probabilistic thing, right? You run it once and you have to run it n number of times, get sufficient sampling to get the distribution. So the current work model is you submit the circuit, goes, runs it, and then you submit the next circuit and so on and so forth. Sometimes you can get in the queue and wait for a long time, which is less efficient. In this case, dynamic research, what it does is once you're done with the circuit, let's say you have to sample 1024 times, then you can perform, compute, reset, perform, compute, reset, perform, compute, reset. That's a more efficient way of doing it. So the mid-circuit measurement becomes very important along with the research. I think some of it may be available in some advanced missions, but in general is still something that that will be available in production shortly. Though this is demonstrated, this capability has been demonstrated. So this is a specific use case. Now, this is a developer roadmap. So building on top of all the things that we learned just now, you would want to see this. This is the software stack roadmap. The previous one that we saw was for hardware. That is on the lower half that you're seeing. This is the Falcon, the Hummingbird, Eagle, Osprey, etc. Now is the software stack that you're seeing. Much like that, you can sort of see the things that I described: kernel developers, algorithm developers, model developers. You're going to have a specialization stack coming through on top of this. And these are some of the capabilities that is talking about. So dynamic circuits are needed. That will be at the kernel level, that at the lowest level. Then you have the algorithmic level where you're looking at natural sciences, finance, and optimization. That actually is more application oriented. It's going to move up to the model level shortly. Once you have one more layer, currently we don't have additional layers. So from the circuits to application is where we are at this time, but you can sort of see the Qiskit runtime is coming, the dynamic circuits are in play. Once that comes, this is going to move up the stack in the level of abstraction. And once we are going to have more cloud-based solutions, you're going to move up the application layer. And here is where cloud-related activities will come, pre-quantum runtimes, and also HPC, which is high-performance computing runtimes. So this is more in the cloud environment. You'll get a layer of developing algorithms falling into that plane, and then application layer moving up one more layer. So currently what you have in Qiskit platform is the Terra, the lower model, and then you have the applications layer. But that's likely to move in the coming times. The application is going to move to the model layer, and you're going to have some more specialization in the in-between layer coming through. All right, let me pause for any questions.
Yes, sir, we have a question here. Do we have a quantum data structure just like classical data structures?
Not exactly quantum data structure. So the algorithms, so in classical, we have data structure and algorithms going hand in hand. Quantum, probably it may come about, I don't know. At this point, I don't, there are techniques, I would say, but not exactly data structures. But at some point, it's possible that some abstractions may come and it may take a shape of a data structure, but at this time, no.
Okay, thank you, sir. Any more questions from participant side? No, I think, sir, we can continue.
Okay, so I'll make one other last comment here. This is useful to remember this. The skills needed at different layers is different. It's important for us to understand that. Not everyone has to have quantum physics background and have to have deep understanding of quantum mechanics for us to do the development here. Kernel developers need to understand the hardware a little bit more, perhaps some knowledge of quantum physics, working knowledge of quantum physics may be immediately needed for doing the right things. Some amount of control theory may come in handy, how microwave skills may come in handy to tune the particular hardware. Algorithm developers don't need to worry about any of that. Some working knowledge of quantum circuit, some deeper insights may help, but working knowledge would be good. They will be in the more algorithmic plane. So you can think of it as some working knowledge of quantum circuit plus classical algorithmic skills will be very useful. At the application layer, you're pretty much like any other application developer. It's just that you need to have a sense for what these quantum algorithms about, where to intercept, how to identify the kernel in your problem. So we're going to still have classical hardware running where the applications are running. You would need to go identify the kernels that can be mapped as to the algorithms in quantum so that you get the boost that you need from quantum. So the application layer will, from a programming standpoint, it will look very similar. That was the idea of frictionless developers that we talked about before. So there, the skills is more computer sciencey, more application type, and if you are a subject matter expert who understands deeply about a particular problem or an algorithm that you use, that will be more relevant. And sort of quantum part of it is you need to understand what that algorithm does and should have deeper insight into the particular application at hand. The skill set will be more in the space of computer science. So as you move up the layer, you don't necessarily need to know all the nitty-gritty details of quantum hardware and quantum physics. You move up the layer and understand this. And very much similar to what we do in a classical world also. Again, I try to bring that up to give you intuition. Not everyone here understands how VLSI design works. Not everyone here, particularly computer science graduate, would know how a VLSI system works, how a hardware is implemented. They don't need to. Things are abstracted out. You can sort of program at a high level. Eventually, it's going to a particular classical circuit and being executed, but how it is, what it is not needed. You don't need to know. And many of computer science folks wouldn't even know deeper level of instruction set architecture, what it means, etc. They don't need to a programming part of it because those are abstracted out. So much like that, you're going to have that layer in time. you're going to become, if you're at model developer level, you don't necessarily need to know all the details or nuances of quantum hardware. It's going to get abstracted out for you. Okay, so I covered most of these points. I'm going to skip that in the interest of time. So we have what is called as quantum network. In the next 5 to 10 minutes, I will talk about the network part, some who's part of the network, what is being done. And then the last section is about the question that was asked before, how you can contribute. So I'll get to that at the end. So the quantum network is basically IBM tying up with different folks trying to use our hardware to do experiments. IBM put out these machines on cloud in 2016. Initially, the idea was from more educational standpoint to have students play with the quantum hardware, run and program it and understand so that you can understand quantum computing a little better. Before that time, all this physical hardware were somewhere in say physics lab and underground. Typically, these kind of hardware are in an underground of a particular department because of obvious reasons here. That was brought out into cloud for people to program. Now there has been a lot of development in the last 5 years. It took a life of its own. Initial idea was being education, become a platform to do research. You have over 300,000 users since use this particular IBM hardware. 700 billion quantum circuits have been run. We are currently averaging something like a billion and a half circuits a day on these machines that we have. We have up to 34 quantum computers. Some of them are deployed, some of them may be in maintenance, but we have up to 34 quantum hardware, over 140 clients and partners. And then important part is 300 contributors to Qiskit. I'll touch on that at the end. Qiskit is the SDK on top of the quantum hardware. And what is most important and interesting is over 400 scientific papers. And this is based on what we could see. There could be many more, but 400 scientific papers have been written using, doing some research on the hardware and on the IBM machines. So this is a significant development using the IBM machines on cloud. A lot of development has happened in the last 5 years. So what we do is that we advance the technology and the platform enabling partners, and the partners then go look for how to use the hardware in terms of their subject matter context. We talked about say Daimler, we talked about ExxonMobil, we talked about JP Morgan and Chase. They have different application areas. They using that in IBM hardware, trying to explore problems in their area and sort of understand how they can apply it. And that's what partners do. They get to access more high-end machines and do their research there. So here is just a laundry list of application area that people are looking at. I've covered some of them in my discussion from before. I'm not going to go into this in detail. So here is our model. So we advance the technology and build a cloud platform. You get algorithmic families, and then you have the applications that come out of it. And there are different users. You can have application developers, kernel developers, or algorithmic developers. So we talked about that. And a lot of these examples I mentioned in my earlier discussion. So a snapshot of one such collaboration. So IBM published a paper on amplitude estimation in probably 2000, mid to late 2018, 19. Then KO, which is a partner, picked it up, advances the method, and publishes with other partners in that group. And then JP Morgan Chase picks up that method and then applies that to option pricing and then publishes that. And then that particular technique is now part of Qiskit. So this all happened in the matter of 18 months or so. So what started from an original idea, went through the university and then to another partner who's a private company, and then it became open source as part of Qiskit platform. All this happening at the rapid pace of development. New ideas are being explored, and eventually some of them will get into the open source platform as well. So here are some of the partners. So you have 12 industry partners. They have specific connotations of what members, partners, etc. mean. But right now for this forum, it's not necessary. I just wanted to flash that. You may be interested in the academic thing. All the top universities, majority of them in US, Europe, and perhaps Japan and Australia are part of this network. The network partner is a paid engagement, so naturally some of more advanced countries have more universities as part of this partnership program. So here is more list of members. So I'm not going to go into the details, just want to let it there for a sec. And I'm going to skip this one. Important thing is building the quantum industry and ecosystem. It's an important part. One is the technology part, but also ecosystem development is just as important to do. One is the access. The first quadrant that you're seeing is access, then skills and training, then industry and economy and research. So all these need to happen for the ecosystem to develop. So for the technology to become practical and be able to productize, you need to have all these happen. All the four essential areas that are jointly being explored, a lot of collaborations and exploring. And for example, this one, the platform that we are in currently and trying to present it here is part of the skills and training platform. That's the engagement we are trying to do here, to talk to many of you, to get you a sense of what this technology about, how do you work with it, what it means, understand what is the industry doing, what is the kind of research happening. So sharing the knowledge, and also in the latter part, you will have training, you will have hands-on programming. So we are trying to develop the ecosystem here, and that's what is part of our objective in this particular field. So I'm not going to go into this access part. Some of you would be programming all right. So we'll leave it there. And some pointers to self-development. I'm going to go into the Qiskit part, which is more important. These are some of the other opportunities available on the researcher program. So in the previous one, you saw some open sources. This is the learning part of it. We have Qiskit channel in YouTube. You have the open source textbook available. And then you have a lot of tutorials available in, again, Quantum Lab. You would want to go give it a try. A lot of education material. On the research side also, there are many PhD fellowships, internships, other programs available for you to pursue. Okay, so how do we build the workforce? And there was a question from before on how can you contribute? I'll address that and then open up for questions at the end. So it's open access, open source, and education. These are the three pillars on which we build this platform. Qiskit is the name, Quantum Information Science Kit. Think of it as an SDK on top of the quantum hardware. It's open source, it's Python-based open source platform, open source, openly governed platform. So you should be able to go to GitHub and search for Qiskit, and you will get all the collection of repos inside it. It's all open source. You should be able to go see it. If you're interested, you can start participating and contribute to the open source community. Qiskit is important. You can do it in many ways. You can move the envelope forward based on your interest and area of interest. You can contribute to various repos. There is the Terra, there is the application layer, and then there is a couple of things, which is the simulator, which is called AIR, and then Ignis layer, which is now called experiments, which is to do the characterization of the hardware. Based on your interest, you can go contribute to any of them and move the open source community and become part of that open source community to do that. Equally important, you can become Qiskit advocate. Anybody can become Qiskit advocate. You just have to sign up. It opens up sometime in July. Sometimes they open twice a year, July and December, I don't know. You basically have to demonstrate some skills and also some contribution, then you can become an advocate. Then you can go talk for the Qiskit technology, the SDK platform. You can become an expert there, and then spread the knowledge in terms of community, be it the developer community, researchers community, based on the interest. You can go build those things. You can contribute in many ways here, and also you can do the education bit as well, since many of folks here are part of academia. Naturally, you can embed some of the Qiskit in part of your lab exercise and programming exercises, perhaps, and teach your students how to deal with quantum programming or become a quantum programmer. So here is an open source Qiskit textbook. You can go to qiskit.org. That's the broad area platform that you want to go. From there, you will have links to GitHub repos. The textbook is available. It's a very interesting way of learning technology. unlike the theoretical way many books are available, here what you are doing is you're programmatically learning it, which is a very good thing. Along with the concept, you get to program, you go to the Jupyter Notebook, run it in simulator, run it in actual hardware, and see the results. That's a very interesting and nice way of learning compute resource that is available. And this is we constantly maintain. In some of it we have in local languages. Developments are happening so that if that is useful or a better option, you can start looking at it. Some of you can contribute here as well. Not all languages are covered. There are special folks who can start contributing towards translation, perhaps, of this textbook in the local language of interest. And once we have sufficient validation of all that done, then we can release in local languages too. So that can come in handy as well. That could be another contribution to the community. I'm going to skip that. I'm going to talk about, I briefly touched on the engagement tracks. This is from the Quantum Hub standpoint. This is where we have IBM interfacing with academia or industry in the paid program. So you can do skills education, application, and research. You can also skip this portion. And then you may have noticed in the last year, we have deployed the quantum computer, physical hardware outside US. All the machines have been in the US. Last year, one was in Fraunhofer in Germany, and the other in Japan, Tokyo. This happened just recently, the physical hardware deployment, and it's gone online shortly. So currently, these machines that we have, the physical hardware, are in US, one in Germany, and one in Japan. All right, that was that. So now I'm open for any questions. So if there are any other questions, I'm happy to answer those questions now. So we have about 15 minutes. As I promised, we have 10-15 minutes. Anybody who has questions, I'm more than happy to take them and answer. It could be any of the topics that I talked about today.
Yes, sir, we have questions here.
Uh-huh.
Yeah. Is quantum computing good for big data processing or real-time requirement, or can also be used for non-real-time requirement?
At this time, so it's there is no one answer to that. I'm going to answer it in 3-4 different ways. Hopefully, that gives a sense of the various aspects or angles to it. Currently, the hardware is still not evolved. It's still a little bit at the early phase where you can talk about real data set and real application. We are not there for us to give it a try. What has been demonstrated right now is certain proof of concept, illustrative examples in quantum hardware showing that it works, and that those algorithms are much like classical algorithms, independent of n. So as the n increases, you should be able to scale out fine. But we don't have a particular application production quality at scale running in a quantum hardware right now to make the case for any of these aspects. However, but that will happen in time as the hardware evolves, and we saw that it's evolving quite rapidly. At some point, there is going to be a breaking point where real problem of interest can be solved at scale. The question of data is very interesting, and this is, I don't think it's a closed discussion or debate at this time. It's not that we have a clear answer to that in the sense, there is a feeling that data processing may be efficient in classical. So that's why if you have heard IBM talk about it, they say classical is not going anywhere. It's going to be with quantum, and quantum is not going to replace classical. So some of the data processing is probably more efficient in classical, and probably some of the kernel of the algorithms can be done efficiently in quantum. But then the algorithms need data too. Right? So in a way, it sort of is this tricky thing where you do need data. Without data, what are they solving? Right? So you do need data. But think of it as I can do a layer of processing, classical processing, and then I know the core of the problem is this, and this. Think of it as a 1,000-row matrix or something. That's hard to do, and that's what I want to go solve in quantum, right? Reduce the problem set, or maybe that 1,000 row thing is in some inner loop of your overall transformation of your application. That's what you want to go solve in quantum. That seems to be the current working model. It may not be very efficient at this point in time, certainly, to consume gigabytes of data and so forth. That may not be the real application at this point. At least I cannot see it that way. So there will be a classical portion, and the kernel of it is what we want to take it to quantum.
Okay, thank you, sir. Next questioning. So, what are the limitations of quantum computers?
So currently, noise is a limitation. That is also determining the kind of algorithms that we want to run in quantum. Remember that, so the way you would want to think about it, at least intuitively, is that I told you that the state space grows like 2 power n, where n is this number of qubits. So if what quantum volume in a way tells us is how much of those state space is accessible to the current hardware at hand. So if I have say 2 power n state space, I'm not able to access all the 2 power n state space. That's the limitation, and that I cannot access all of that is probably because of the noise that we have. The more the state space that is accessible to me, it is good, because then I have the full power of quantum, full power of what quantum can provide at my disposal. Then I can probably then solve certain problems of interest at scale. Because of the noise, it's the subset of states is what is available to me, and then I have to do the processing. Then I have to navigate how best to use that state space and do the transformation so that I manage the noise at hand. The current particular generation we are in terms of the overall scheme of things, till we get to the fault tolerant type threshold, which is 10 power minus 4, error rate of 10 power minus 4 or below, we will be in that regime where I cannot do error correction, and therefore self-correction is not possible. And also I don't have millions of qubits that is needed for me to do that error correction of significance. So we'll be in this regime that we'll have to deal with this kind of hybrid algorithms, deal with noise. And so that's a limitation and an opportunity, because you saw that the number of qubits, everything is increasing quite rapidly. When it becomes production quality and useful, it's really there is a big contribution coming from the software, how best to leverage it. So that's an opportunity. But the limitation is the hardware. It's growing exponentially, but I cannot run things at scale at this time, given where we are at that time. So I would say that the lifetime is another part. Again, noise. It's in a way related to noise. That is, how long I can keep the quantum properties alive is also a function of it. Those are the two main computational part that I can see. That is of that's a limitation at this point in time.
Okay. Other than superposition, entanglement, and interference, is there any quantum mechanism concept still not yet explored?
Instead of quantum mechanical, there are many quantum mechanical properties in physical quantum things. So let's not generalize in that sense. I will make it quantum computational properties, if I want to call it that, rather than quantum mechanical. Quantum mechanical could mean many things. High energy physics has many such quantum properties. You can talk about many quantum properties, which is explained ultimately by quantum physics. But I don't want to use the phrase quantum properties, but I will say quantum computational properties. The key element is entanglement. Superposition and interference are seen in classical domains as well, but then in the context of quantum computing, quantum computational properties that we require is superposition, entanglement, and then interference effect is there. And then finally the measurement, it's more a postulate, but those are the key elements of quantum computational properties, and I think we are covered. In a way, how you know that is because you can then ask, so it's been shown that quantum computers can be universal. The universality argument is I can go and do, if I have certain set of gates, then I can perform any quantum logic. Much in similar lines to binary, right? In Boolean, you know, if I give you a two-bit NAND gate, it's universal. That means I can do any binary logic using that. Much like that, we have set up gates. If I have that, then I can do any quantum logic out of it. So we are covered on that front, and that requires us certainly entanglement is a key element.
Will it handle repetition of state space without recomputing?
It depends on how you construct it. One thing to note, which I have not talked about, is you cannot copy a quantum state. Because I cannot know the quantum state, I cannot copy it either. So for example, if some of you who may have um, classical circuit knowledge, you know that you can take a signal and do a fan out of it, and then you can do computation and so forth. You can't do something like a fan out. Fan out is nothing but I'm copying it into two different states in a way, if you wanted to, though it's not going through a latch, but conceptually at least I'm taking a fan out and making a two copy of it and then taking it along. I cannot make copies of quantum state. I can certainly put that in what is called as a quantum RAM, QRAM. You can retain it and then use it, but I cannot copy it. So once I start using it, it has to keep moving forward. But then to your answer, I can always generate that state perhaps because I know the logic that got me there. But reuse of it without, I can't make a copy of it. So I would say you cannot essentially reuse that, but you can delay it and do the computation later.
Any training program provided by IBM in quantum computing?
So for those of you who are not aware, we are doing an NPTEL course in 2 weeks time, August 23rd through September, late September. It's a 6-week course. This is jointly being done with IIT Madras and IBM. It's available. It's a 1-unit course. It's FDP approved. So you can go register with it and learn. This is one of those programs that we are running in India in NPTEL platform. It's a e-learning, as you can see. And then probably we may do certain workshops in the latter part of the year. Currently, we don't have anything scheduled at this point in time. We may do certain workshops where we teach how to do programming of these hardware and latest of the algorithms, etc. So, but for the present, we have an NPTEL course coming up the starting 3rd week of August. It's a 6-week course. So encourage everyone to go register, and also those of you who are teachers, maybe you can encourage your students to go register. I will leave the link with the host here. They can share it with you, and whoever is interested can register.
Sure, sir, we'll share it. Yeah. What is random circuit in quantum computing? Give an example for random circuit. What is structure of random circuit?
So something in the chart, I'm missing the context. What would be a random circuit?
There's no context, but the question is asked by Raj.
If somebody can give me, whoever is asking the question, if you can give me the context of that question. So random circuits typically, at least in our case that I am aware of, we use it for characterization of the hardware. So that we know how well it is doing. So for characterization, we do randomization of circuits in our benchmarking. It's called randomized benchmarking. It is used in that context, but I don't know the context of the question in terms of random circuits.
Yeah, here 2 questions actually almost similar. Any interesting case studies or small projects which can be given to the student as an academic project on quantum computing?
So I encourage you all, there are a couple of things I wanted to show. Let me show you that. I'm trying to bring up a page. Let me bring that up. I'll share that. Okay, let me share my screen for a second. I wanted to leave you with few pointers so that you can start looking it up. So here is the qiskit.org. This is the link that I've been talking about for a while. This is the overall platform. As I mentioned, this is an SDK for the quantum hardware. It's open source, openly governed. You can go look it up. There is a lot of links here. Yeah, and then you can also go to the GitHub repo from here. We are present in Stack Exchange. There are Slack channels available, so I encourage you all to go take a peek. The important part is few things I wanted to show here. So if you go to the learn part, there are many links available. I'll get to the question that was asked. The reason I'm pointing this out is there are many accessible information available. These are not very advanced in terms of the content. So first is the Qiskit textbook. I would go have you look at it there. There are some questions at the end in some cases. In other cases, you can take what was taught in the textbook perhaps and tweak it and make it into some project perhaps. There is this introduction course that you can take a look, and there is a good whole lot of material which is the introduction to quantum computing and hardware. The other part is the tutorials part. I encourage you to go look it up. There are a lot of useful Jupyter Notebook tutorials available. Again, the same principle. You can start with the tutorial and then tweak it for your need and see if you can make it into some project for the students to go look at. So I would start from here and look up these information. Then there is also Coding with Qiskit. It's a YouTube channel. You can go look it up. And the Qiskit YouTube channel has many more advanced videos too, right from beginners programming tidbits all the way till research level discussions. So that's a good source for information. But from coding standpoint, Qiskit textbook is good place to look at. Tutorials is good place to look at. Those are Jupyter notebooks, and then you can start playing with it. The other thing I would say is the community. So if you go to the community, there are events and advocates. That's one. But there is a repo called Qiskit community. If you go to GitHub and search for Qiskit community, you will find community.qiskit.org. So this is a community outside of the main Qiskit, which develops a whole bunch of things. So for example, you will have additional tutorials that is not there in the Qiskit available here. You will have a whole lot of Jupyter notebooks in this list. So there are different challenges that are run. You will get those repos here. You can go look it up. Or there is web components. Qiskit textbook is available here. Translations. But I saw there was one. Yeah, Qt codes is another thing. This is for Surface Code. Looking for one where tutorials was there in this community. Maybe you can search for the tutorials in this community. So all the different challenges that are run by Qiskit community gets captured here. You can go look up those challenges. Perhaps you'll get the Jupyter notebooks for them. And then from there, you can sort of tweak it and see if you can create some exercise for your students. So these are good starting points, and there is a lot of information available here.
Okay, in continuation to this point only, they are asking, is this course are free?
The NPTEL, is it? Which course are they talking about? So if they mean Qiskit, what I showed in Qiskit Learn, yes, it's all in YouTube videos. You should be able to go see them.
Okay, yes. What does double entanglement result in?
I don't quite understand that question. What does double entanglement mean? Can somebody can they clarify what is double entanglement?
You can, Minal, you can allow them to unmute and talk if the.
Yes, yes, Kavita madam, if you are there, please unmute yourself and you can talk.
I think we should sanction them. You need to sanction them, right? I think.
Yes, yes, we are doing it, sir.
Okay, so while that comes along, so here is the NPTEL course. I don't know. This is FDP because I don't know whether there is a cost involved in this or not. We are offering it with IIT Madras.
Mostly the fees will be for
Yeah,
the
it is
examination.
1,000 rupees. Yeah,
That's an
optional
examination.
fee, examination fee.
Ah, yeah, that's an examination fees, right?
Yeah, but I don't know if the course has any money. I don't think so, but it's
Normally it will not be having, sir. Normally it will not be having.
yeah,
Yeah.
yeah. So this one should not have. And if the question was regarding this, it's all available. So for example, you can go click on this one. There's a lot of information here. Uh, these are all available. You can just go click on it. It goes to a YouTube video. You should be able to see them. So all these are available openly.
Kavita, madam, we have unmuted. I think.
Simulation pack. Maitri ma'am can see. Hello, sir.
Yes.
Sir, double entanglement in the case, first placing a Hadamard gate and then placing a C naught. Again, if I place a Hadamard and a C naught, what will be the result?
It depends. You actually build that circuit and see what you get. It's a transformation. So typically, you need to work out the math to see. What you're seeing is when you do double, so when you do Hadamard and a C naught and then Hadamard and a C naught, remember Hadamard is Hermitian. So two Hadamards means getting you're getting identity. So this, after the second Hadamard, you will get zero state. And so the C naught that you apply after that will not do any inversion. So all the state that you got, the Bell state that you got from before will just carry through. Uh, you work out the math. So once you have the Bell state and then you apply Hadamard on that Bell state, so now we are in entangled state, then you apply Hadamard on it and see for each bit when you apply Hadamard, Z goes to plus and 1 goes to minus, and then just expand that out. And then when you get that out, separate that out as 0 and 1 and see when 0 shouldn't do anything and then 1 should flip it. And then when you do the C naught, see what happens. The other thing that you can do is you can actually build it and see what happens. So let me see if I can show that if I have time. That's where I think having actually a platform, a programming platform where you can actually code this up and see will be very useful. So let me see if I can share. Okay, so hopefully you can see my screen. I am in quantum-computing.ibm.com. Hopefully many of you have an account with quantumcomputing.ibm.com. You can log in there. So you can go to, this is better done in a visual example. So let's create a new file. So you'll get the Bell state with this, and then you apply this. Oops. Okay, so let's just walk through this. So at this point, you get the Bell state, right? So first was, let's go back the previous Hadamard. You get, so let's remove this qubit. I don't need this qubit. So before I do that, so let's remove this. So I have only 2 bits. So it goes from 00011011. So let's go inspect. So first is Hadamard. So Hadamard should put the qubit 0 in superposition. Qubit 1 will be still in 0 state. Note that the default state is 0. So you will have 0, 0. At this point, you will have 0 plus 1, and this will be 0, right? So you will have the first qubit in 0 and 0 plus 1, and the second qubit, which is the MSB, is in 0, right? And then you go to C naught. Now you see the Bell state. You get 0, 0, and 1, 1, right? That's what you are getting. So you can also look up in the Q sphere. I'm plotting it in state vector. And we can go next. So here is where this is the state vector. This is the state that you are in at that point in time. You are in superposition all the 4 states. And then let's go to the next C naught. Then you get the answer, and then let's put some measurement result and see the result, what we get. So let's put the, what is that measurement? Z basis. And then what you get back is 0, 0. Right? So I encourage you to play with this so that you can also see the state space evolve, and you can run this thing in actual hardware if you have not done so. So yeah, this one is a simulator that you ran, so I can just run it in. So one of the machines that I have access to, this is in the actual hardware, and then just run it on there. It's going to take a little bit of time. Once it is done, we should see our expected answer is it should be in state 0, 0, but it will not be exactly 100%. You will see that in actual hardware, you won't get 100%. So important part to remember in this is quantum is slightly different from classical because of the quantum logic that we have. So for example, so while that is going on, let me delete these guys. A simple case is this one. So let's take, for example, many of you would know Hadamard is like a coin flip. The equivalent intuition that you get is that it's a coin flip, right? So you think, okay, so I'm in, I'll be in equal probability of getting 0 and 1. So what if I put one more Hadamard? What would that lead to? Would that mean 25%? What does it do, right? If I had two coins, for example, in classical case, this is where the intuition doesn't carry over. So probably the question of double entanglement was in a way related to classical way of thinking. So if you had one coin and you get 50-50, and then now you had two coins to do that, what would you get the answer? So the intuitive answer in classical sense would be, okay, 25% 0, 0, 0, 1, 1, 0, 1, 1 equal. But in quantum case, what happens is that because of quantum interference effects, what was 0 plus 1 then goes back to 0 at the end. It cancels out. And then you get just 0, 0. And it's not like 0, 0, 0, 1, 1, 0, 1, 1 with equal probability. That's not what you get. So because of this simple thing where this cancellation happens, it sort of brings out an important property that the classical intuition directly doesn't carry over to quantum. The logic of it is slightly different. The best way to do it is actually build the circuit, look at it and see how it goes. And maybe the second best thing is to actually calculate that mathematically. And what I showed you, that it cancels out, right? We showed that the answer was 0, 0. If you work it out mathematically, you will see that it does get that answer. So let's see if my job did it. Is it still waiting? It's in the queue. Okay. What? 15 hours? No, that's not going to happen. It's going to happen much sooner. Okay. You can give it a try. Whatever I just did, you can do exactly the same thing and kick off a run and see it run, and you will be able to understand. Hopefully, I answered the question. Any other questions?
No, I think so. That's it. Yeah.
Okay. Yeah. Thank you.
Sir, I have a question. In the Indian scenario, you're watching the progress of quantum computing. So the government is also going liberally, announcing the budget of 8,000 crores and all. So what is your viewpoint, sir? Like how the industry is progressing? There are a lot of startups are coming up, and what is the potential of doing this study, and a student going out of engineering college, if they go with the quantum computing knowledge, what is the chance of he is getting placed and all, sir? Can you please throw a light on that?
Right. So there are many things there. So one thing is that the funding that you talked about is for quantum technologies, not quantum computing exclusively. Quantum technologies involve building the hardware, doing sensing. Quantum computing, certainly there, communication is also part of it. It's a gamut of things. So what that 8,000 crore that you mentioned is for quantum technologies, which includes all of them. Now, quantum computing is but one part of it, but a significantly important part. In terms of the skill, one of the reasons for while the charter is very, very wide in terms of from a government standpoint, and rightly so, um, the one of the important thrusts is also skill development within the community and within the country of having the right skill set in this area of quantum technologies broadly and quantum computing in particular. Because, as you know, the software sector is significant in India. The IT sector, the services sector are like 55% of global services sector. So it's a key leader in that area. And if one of the now there are many projections to quantum computing in terms of what is the potential that we are seeing. So it is certainly it's estimated that it's going to become in billions of dollars in the coming decade. You're going to have billions of dollars worth of different. The industry is likely to become billions of dollars worth. How much of it could range from 25 to 75, whatever the estimations are. So this means that there will be work involving how to deal with this quantum hardware and programming the quantum hardware. So from India's standpoint, given the quantum computing, within the quantum computing context, and within that the software skills context, it becomes important to upskill and learn this skill because the quantum hardware in all likelihood is going to become quite mature in time to come, and you're going to have the industry building around it, and therefore the skills will become important. And one of the reasons why that kind of push is being done at the government level is when that comes, we don't want to miss the bus. We don't want to lose the leadership position in the software sector in particular and be able to grab any opportunities that you'll get, industries that you're going to create. And the skills that is needed is what we want to invest on now. Currently, for software programming of quantum hardware, as I mentioned, we don't have it at a production quality deployed level. So the opportunities will be limited to, say, startups and other things that are exploring possibilities, etc. But in time, you're going to see more and more investment coming through across many industries, and there will be requirement for these skills. I feel that skill will be highly valued over and above the normal skills because it's something unique. And that will also be a key important unique value proposition for a particular developer candidate or a student to have. And those of the students who are starting their journey in this space, in the next, by the time they graduate, perhaps there is only more demand. And in time, certainly that skill will be highly valued, is my opinion.
Thank you, sir. Thank you. Minal, do we have any more questions?
No, sir.
Okay, okay. Then
Yeah.
formally wind up the session.
Yes, sir. Yes. So, Dr. Shesha, thank you so much for your wonderful presentation, which has given the overall view of quantum computing and its application. And thank you for accepting our invitation for this faculty development program. Thank you, sir.
Sure. Thank you. Thank you for the opportunity. Thanks for RVC and Professor Satish Babu for the opportunity, and thanks for all the audience members participating with my video and also with the questions. Thank you.
Thank you, sir. Thank you, Dr. Shesha. I will wait for Archana and for joining, sir, 11:45.
Yeah.
Okay, sir.
Okay. Thank you all.
Thank you, sir. Thank you. Have a great day. Thank you. Bye-bye.
Bye.
Participants, the next session will be at 11:45. I'm correct.